Okay, so it's the 12th, and we're talking about derivatives involving e to the x. So let's do it. And thank you for that mic thingy. All right, so what's the derivative of e to the x?
E to the x.
E to the x. Okay, that's just too easy. I'm really asking this. What's the derivative of a to the x? A may not be e, but a is a constant. Like 2 to the x. No? Okay, well, remember logarithmic differentiation? What if we take the log of both sides? What do you get? ln y equals x ln a, but ln a is ln a. Sorry, I'm thinking something else. Okay, is that correct?
Yes.
No? The derivative of wait. That is correct. I'm sorry. I'm going crazy. I'm thinking of something else. Excuse, please. Okay. Now, what if I differentiate both sides explicitly with respect to x? Y is a function in x. What do you get? What's the derivative of ln of y? Not yet. What's the derivative of ln y? I'm trying to get dy dx in here somehow. I need y prime, right?
Derivative of ln y
is 1 over y d y dx, because it's chain rule, right? And what's the derivative of a constant times x? Like 2x. What's the derivative of 2x? 2. So what's the derivative of ln a x? ln a, okay. So can you tell me what dy dx is by itself? How do you get this alone? Multiplied by y, right? Okay, so y prime is ln a times y, but who's y? A to the x. Okay? So this is really a special case. I'm going to separate this. This is a special case of this. Because what if a was in fact e? ln e, which is 1 times e to the x, is the same thing. So this is a special case of this more powerful rule. Okay? So let's keep that in mind. So the derivative of a to the x is ln a times a to the x, sort of like a little correction factor. So what if I asked you the following? If y is 3 to the x, what's dy dx?
It would be ln 3
times 3 to the x. Perfect. That's all right? So now you know this little fudge factor, right? All right, how about this one? What if I'm integrating 2 to the x? And remember, you know how to get an antiderivative. You got to think of something whose derivative is 2 to the x. What do you think?
Oh no.
Any ideas? Huh? Not e. Yeah. I know the derivative of a to the x is ln a to the x. Do I know the integral of a to the x? Would it be? Look, if it's 2 to the x is no good, right? How do you test if you have the right derivative, antiderivative? If you differentiate this, you better get that. But you don't, because the derivative of this is what? ln of 2 times 2 to the x. So it's off by a factor of ln of 2. So fix it. That's all. So when you differentiate, you multiply by this correction factor. When you integrate an exponential function, you divide by this correction factor. Okay. So now we know a whole bunch more integrals and derivatives and stuff. Right? Alrighty then. So take a look at this part 1 question. This is 93, AB1, number 28. They had scientific calculators, but they didn't have graphing calculators. They want this answer to the nearest 3 places as a decimal.
What's your favorite color?
It changes. I don't know, maybe I think it's red. I don't know. Why? Why? Okay, good. All right, so take a look at 28. How do you suppose you could get this to the point where you can plug it into a scientific calculator? Okay, what's on the sheet I just gave you? Okay, here it is. Okay, this is 1993, AB Part 1, Question 28. Okay, it says, what's the area from 1 to 500 under the curve 13 to the x minus 11 to the x? but wait, there's more, plus the area under the curve from 2 to 500 of 11 to the x minus 13 to the x. Right, do you see that on the sheet? That's what they have? All right, so how do you do that? Well, this is a pain because you don't have a graphing calculator where you can do like second 7, right? You have just a scientific calculator. So you got to get to the point where you're just plugging in numbers and you can type that into your calculator. So let's try and simplify this a little bit. First thing you should notice is there's a relationship between these two integrands. They're different, aren't they? But how are they related? They're opposites, right? So could I just change this to subtracting if I change the order of the subtraction here? Okay. Now why is that useful? 1 to 2, right. If I take the area from 1 to 500 under this curve, minus the area from 2 to 500 under the same curve, I'm only talking about the area from 1 to 2. All right, so, so you end up with one integral, and you don't have these insane limits of integration anymore. That makes it a little bit easier. All right, so let's anti-differentiate. What's the antiderivative of 13 to the x? That's the derivative. It's 13 to the x divided by ln 13. There you go. Minus 11 to the x over ln 11. Perfect. Okay, we're going to evaluate that from 1 to 2. So let's do it. All right, so plug in 2. 13 squared over ln 13 minus 11 squared over ln 11. Quantity minus, plug in 1. 13 to the 1, or 13 over ln 13 minus 11 to the 1, or 11 over ln 11. That's the correct answer. That's the exact answer. But that's not what they want. Look at the choices. They want a decimal rounded off the nearest thousandth. So that you can plug into any calculator, can't you? You don't need a graphing calculator for that. So let's ask Hal to do this. Let's pretend that Hal is scientific. So we'll just do the home screen, and we won't do any special second 7s or anything. All right, so let's plug this in. Let's see. Quantity. 13 squared divided by the ln of 13 minus 11 squared divided by the ln of 11. That quantity minus 13 over ln 13 minus 11 over ln 11. And of course we don't want that. Diamond, enter. 14.946. Choice B, isn't it? Good, perfect, there you go. So that's how the first calculator exams were. You had to use a scientific calculator. You had to reduce it to the point where you can just plug it in and get numerical results, and that's it. Okay? But that was choice B. Any questions how we did that? All right, take a look at the back of that sheet. A free response question, 81AB4. Okay, you ready? All right, ready or not, here we go. So 81AB4, wow, that screen is so bright, it's like, wow. That's red? Okay. It says, let f of x be 5 to the square root of 2x squared minus 1. Part A, is this an even function, an odd function, or neither? How do you know? Excuse me, are you paying attention? Okay, what? You could graph it, but again, this is 1981. We didn't even have scientific calculators, much less graphing calculators. So what else? When you assume, you make an ass out of you.
Okay, so it's going to be radical 2x
And me.
squared minus 1 ln of 5.
I'm not doing any differentiating or integrating yet. I'm just saying, is this an even or odd function? When you graph it, does it have y-axis symmetry, origin symmetry, or neither?
I'm going to guess even.
How do you know? There is a way of doing it. Well, think about it. What if you have like a parabola with y-axis symmetry? What do you know about every single point on that curve? F of x equals f of negative x.
Oh, yeah.
Remember this? College algebra, yeah. What about an odd function, like a cubic? F of x equals negative f of negative x.
Yes.
All right, so let's see what negative f of negative x is. And we're talking about every single x you can plug in the domain. We're talking the entire curve, right?
F of x equals f of negative x.
All right, so is it? Well, let's see. Let's plug in negative x, see what happens. 5 to the 2 times negative x squared minus 1. What happens when you square negative x? It becomes the same as this. So f of negative x is f of x, meaning even. Even function. Okay? That's part A. Part B. What's the domain of this creature? Okay. F of x is 5 to the 2x squared minus 1. How do you figure out what numbers you can't plug in? Or what can you plug in? Let's put it that way. Can you?
Is it greater than 0?
Yeah.
I want things in the